Welcome to the Limiting Reactants podcast. This podcast covers sections 9.3 and it's on pages 296 to 303 of your textbook. The Limiting Reactions podcast really, you need to have a very good understanding of stoichiometry to be able to do this podcast. Limiting reactions essentially is just an application of stoichiometry, something that chemists actually use stoichiometry for in their calculations and in their reactions. So the idea of limiting reactants is actually quite simple. The limiting reactant is the reactant that is used up or runs out first. And it actually is the thing that's going to determine how much product we make. So the simplest example we have of a limiting reactant is with hot dogs. When you buy hot dogs, they come with like 10 hot dogs in a pack. But the buns only come 8 buns to a pack. So if we buy one package of hot dogs which has 10 dogs and one package of buns which has 8 buns, we can only make 10 total hot dogs. I'm sorry, excuse me, 8 total hot dogs. I don't know why I just said 10. That doesn't even make sense. All right, so 8 total hot dogs because we've got 10 dogs but 8 buns. So the buns are actually limiting us on how many hot dogs we're going to make. So you could also write that little equation out that one pack of dogs, one pack of dogs? I don't know where that came from. Anyway, one pack of dogs plus one pack of buns is 8 hot dogs. So our limiting factor in the hot dog production is the buns. Of course, they sell the 12 package of buns too, but then you're short 2 dogs, and that's no fun. All right, so anyway, we can do similar figuring with chemical equations if you know how much starting material of each reactant that you have. Okay, so there are certain steps here to determine the limiting reactant. Number one is that you have to convert the amount of each starting material to grams of one of the products using stoichiometry. So when you do these problems, you're going to be given either grams of both starting materials or moles of both starting materials, and you have to convert each of them into grams of one of the products. After you've done that, you have to determine which of the reactants produces less of the product. That reactant is the limiting reactant. So the amount of product formed by the limiting reactant is the maximum amount of product you can form by the given amount of reactants. Okay? So you could technically form less, and most equations, most reactions actually do form less than what you calculate you should create. But that is the maximum that will be produced. So to sort of reinforce this concept, we're going to do a practice problem where we actually convert an amount of our starting material to an amount of product. So we have given to us 18.1 grams of NH3 and 90.4 grams of CO2. What is that? No, this should be CuO. Okay. So really, let's read this and read it correctly. 18.1 grams of NH3, so 18.1 grams of ammonia, is reacted with 90.4 grams of CuO, copper oxide. Technically, copper 2 oxide, for those of you keeping score at home, according to the following equation. 2 ammonia molecules react with 3 copper oxide molecules to make a nitrogen molecule, 3 copper molecules, and 3 hydrogen molecules. 3 water molecules. Wow, I can't speak today. Okay, so another way to read this would be 2 moles of ammonia react with 3 moles of copper oxide to produce 1 mole of nitrogen, 3 moles of copper, and 3 moles of water. Our question is, how much copper is produced? So how much copper, right here, copper, how much of that is produced? Okay? So what we have to do is set up a stoichiometry equation for the 18.1 grams of NH3 and for the 90.4 grams of copper oxide. So we're going to have two-dimensional analysis setups here. Okay, so first of all, we're going to start with 18.1 grams of NH3. For some reason, this didn't write my G. There's a G. There we go. And we're going to set up our little boxes here. So here's the first one. We've got 18.1 grams of NH3. We're going to have grams of NH3 on the bottom here. And we want to convert NH3 to moles. So we're going to use the molar mass of NH3, which, when you add up nitrogen and 3 hydrogens, is 17.04 grams. And that's for 1 mole of NH3. All right, so we're going to continue our problem on, because if we stopped there, we've canceled out grams of NH3. Wonderful. But we're left with moles of NH3. We need to get all the way to grams of copper. So we can convert moles of NH3 to moles of copper using the balanced equation. So moles of NH3 needs to go on the bottom of our dimensional analysis setup here, and moles of copper needs to go on top. And the numbers we're going to use for these, the moles of copper, comes right from the equation. So this is a 3, and the NH3 is a 2. I won't draw a line there because I think that'll make it just look ugly. We don't want that. All right, so if we canceled out units here, moles of NH3 cancel out. We're left with moles of copper. We need to go one more step and get grams of copper. And moles of copper is going to be on the bottom, so we can cancel everything out. And moles and grams, 1 mole, we need to know how many grams of copper there are for 1 mole. This we just grab right off the periodic table directly because it's just an element copper. 63.55 grams of copper to every 1 mole of copper. And when you calculate this out, it comes out to be 101.255 grams of Cu. And when we round it using significant figures, our starting number only had 3 significant figures. So our final number has to have 3 significant figures, 101 grams of Cu. Now some of you might be wondering, why didn't I take into account the 1 significant digit from the mole ratio here? But this technically is a definition. Okay, so we're actually defining 3 moles to 2 moles. So anything that's a definition or a count, remember, we have infinite numbers of sig figs, and those don't play into the numbers of sig figs that should be in our answer. So anyway, rounding with sig figs, it's 101 grams of copper. So that's how much copper we can produce, right? Well, we can't really be sure because we're starting with 90.4 grams of copper oxide. So why don't we convert 90.4 grams of copper oxide to grams of copper as well? Because we might get something different. I don't know though. It's got to be the 18.1, right? We're starting with so much less. So we're going to set up another dimensional analysis problem with 90.4. This should have a little grams here. Grams of copper oxide. We're going to set it up basically the same way. The setup is really similar, except we're starting with grams of copper oxide instead of grams of NH3. So 1 mole of copper oxide, and the molar mass of copper oxide is 79.55. So we're going to continue the dimensional analysis here. Now we're going to use still 3 moles of Cu, because we're trying to convert to grams of Cu. But now on the bottom we need moles of copper oxide, which is also a 3 from the balanced equation up above there. And then our final step is exactly the same as it was above, 63.55 grams of copper to every 1 mole of copper. Units, let's check them. They cancel out. Grams of copper oxide, grams of copper oxide. Moles of copper oxide cancels out with moles of copper oxide. Moles of copper cancels out with moles of copper, and we're left with grams of copper. Perfect. The answer to this problem, when you calculate it all out, is 72.218 grams of copper. And rounding with sig figs, it's really 72.2 grams of copper. All right, so we've got two different amounts of copper that we can make. Which one of these is less? The second one. All right. So even though it seems like we're starting with so much more starting material, the 72.2 grams of copper that we make from the 90.4 grams of copper oxide is the amount of copper that is actually going to be produced from this reaction. So if we know how much copper is produced, what is the limiting reactant? Well, the limiting reactant then is copper oxide. CuO is limiting. So on your practice problems that you have to do in your packet, you're going to be asked to determine the limiting reactant. It'll say which reactant is limiting if you're given, such and such starting amount of reactant A and such starting amount of reactant B. And basically what you need to do, what we did here, is go through two whole dimensional analysis setups to convert the amount of grams of each starting material to grams of the product that you're trying to find. So in this case, we're trying to find grams of copper formed. We found out that 90.4 grams of copper oxide produces only 72.2 grams of copper, whereas 18.1 grams of ammonia produces 101 grams of copper. So the copper oxide reactant is limiting when we have these amounts. All right. Copper oxide is not always limiting. It's only limiting when we start with these amounts. So the limiting reactant is entirely dependent on your starting amount of each of your reactants. If you change starting amounts, that means you have to go through and do the calculations over again. Okay? So what I would like you to do at this point, we're pretty much done with a limiting reactant podcast, so write down any questions that you might have. This can be a little bit confusing. It's okay if you're not quite all the way there yet. There's lots of practice problems for you to try. We've got the book you can look through, and of course, like I said, write down your questions and ask your teacher and get clarification so that this is as clear as possible. If you can do limiting reactants, that means you've got a real good grasp on stoichiometry as well. So it's kind of a big concept. So, if you're getting it already, that's great. If not, a little bit of work, and I'm sure you'll get there.